In the science storyline approach used in OpenSciEd, the sequence of activities are designed to make sense to students. The storylines were developed based on the inputs from hundreds of classrooms and the questions students actually asked. Let's dig in and see how the story of Unit 8.3 unfolds. OpenSciEd units are organized into lesson sets, or groups of lessons focused on figuring out a part of our phenomenon. At the end of a lesson set, students put together their ideas to explain what they can at that point. So in the first half of Unit 8.3, students investigate how can a magnet and a coil wire interact through forces at a distance. Next, lesson set 2 is focused on figuring out how energy is transferred through electromagnets and how it is transferred across the space between the magnets. And lesson set 3 is another short lesson set where students are investigating and then explaining factors that affect the strength of magnetic fields. Let's dive into lesson set 1 and see how this unit kicks off. In lesson 1, our anchor, we observe a speaker system with a magnet and a coil of wire moving back and forth without the parts touching. We develop initial explanations of how this might work. We write driving questions for our DQB and come up with ideas for investigation. We're wondering, what causes a speaker to vibrate? How can parts of the speaker system cause sound without touching? So in lesson 2, we experiment with different objects to establish that while certain metals do interact with magnets, such as other magnets, the copper coil does not. We notice force pairs between the magnet and the coil only when the coil is hooked up to a battery. So we know from our collisions and our sound units that contact forces transfer energy through collisions. But where does the energy of the moving coil come from if the parts of the speaker are not touching? In lesson 3, we wonder how energy could transfer between parts of the speaker when the parts aren't touching. We write hypotheses that predict the cause and effect relationships, and then we test them with 2 whole class investigations. We observe that when we block the air between 2 magnets or remove it altogether, magnets still exhibit some of the interactions when they get close to each other. Meaning, the energy that makes magnets move does not get transferred through the air. Now that we know our hypotheses about the role of air are false, we really aren't sure what's going on in the space between the 2 magnets. We need some new ways to visualize what's going on in this space. So in lesson 4, we define and investigate this mysterious magnetic field with objects like iron filings and compasses. Through this, we see what the magnetic field looks like and that it's not the same in every location around a magnet, but they all seem to have their own 3D shape. Not only that, but the forces in the magnetic field have a direction that we can model with diagrams and computer interactives. So now we're wondering how the magnetic field responds when there are 2 magnets, or a magnet and a coil that are near each other. In lesson 5, we see that when we add a second magnet to the computer interactive, the space of the magnet field changes depending on the orientation of the magnets to one another. We make diagrammic models of the fields and come to consensus around how to represent the fields. We figure out a lot about attractive and repulsive forces in the magnetic field, but it was hard to tell what happens when we move the magnet and the coil closer together. In our investigations throughout lessons 2 through 5, we figured out that invisible magnetic fields are responsible for the interactions that we saw between the magnet and the electromagnet in the speaker. Next time, we want to pause and put together some of our ideas to explain how this happens, which will also help us to determine if there's anything else about how this speaker system works that we still need to figure out. In lesson 6, we apply what we've figured out about properties to explain a related phenomenon, explaining how a doorbell works. This is the midpoint assessment for the unit. We still have a lot of gaps in our model that we want to investigate around the electromagnet. How does it work? And how does it produce both pushes and pulls when it is connected to a music player instead of a battery? We have some ideas we want to test. That leads us to lesson set 2. In the second half of the unit, we shift to figuring out how energy is transferred through electromagnets and across the space between magnets. In Lesson 7, we plan and carry out an investigation using a cart on a track to determine how changing the distance between two magnets affects the kinetic energy transferred between them and the amount of energy transferred into and out of the magnetic field. So at this point, we think energy must be transferring out of a battery into the electromagnet. But the speaker doesn't have a battery. It's connected to a music player. We aren't sure if these are the same thing or how they are related. In Lesson 8, we vary the volume and frequency of sounds being produced by a sound generator on a computer and observe the effects. We gather information using various materials, including light bulbs, to help explain how changes in the electric current produced from the computer results to changes in a magnetic field within the speaker system. At this point in the unit, we figured out so much, and we're ready to put our energy-related ideas together to update our models and help explain our speaker system. In Lesson 9, we add to the list of cause and effect relationships and construct a class consensus model to explain these relationships and how they work together to produce the patterns of movement we see in the speaker. After a brainstorm and a reading jigsaw, we wonder what we could do to make magnetic forces strong enough to lift trains and cars. By the end of this lesson, we've learned about some very large applications for electromagnets, but our electromagnets can barely move a paperclip. We revised some of the questions on our DQB about the strength of magnetic forces that we want to investigate next in order to figure out how these very big devices can work. And that brings us to Lesson Set 3. In Lesson 10, we co-design and then carry out an investigation using a digital scale to test the relationship between distance and magnetic force. We analyze graphs to determine the relationship between distance and magnetic force between two magnets. We figure out that when we change the distance between two magnets, the force pairs between them, attractive or repulsive, gets stronger when they are closer together. But we have a lot more questions about what causes changes in the strength of magnetic forces. We want to divide and conquer to answer those questions through some investigations. So in Lesson 11, we do just that. And we learn that when we increase the size of a permanent magnet, increase the number of coils in an electromagnet, or increase the current, we can make the forces between magnets stronger. We have figured out so much that we are ready to take stock of where we have been. We will also have an assessment of this unit where we are going to have an opportunity to demonstrate how much we've figured out about forces at a distance, designing investigations, and cause and effect relationships. Finally, in Lesson 12, we take stock of how far we have come and apply our new ideas about the strength of forces, both the speaker and the other electromagnetic applications we have considered. We revisit our driving question board, take one more time to try to answer our remaining questions, and then finally, we take an assessment. So that's the storyline for this unit. It's designed to follow students' questions and build big science ideas one step